Good evening and welcome to the Q&A session 14 from the chapter of moving charges and magnetism. This session is in continuation of the session number 13 in which we have derived the equation for the magnetic field at a point on the axial line of a current carrying loop. So the question for this session is written here on this board, and the question is: the magnetic field normal to the plane of a circular loop consisting of n turns and radius capital R is measured on the axis of the loop and at the center of the loop. So if the current flowing in the loop is I, then the ratio of magnetic field at a very far distance, which is equal to R, from the loop center on the axial line to that at the center of the loop is. So there are four options, and we have to find the correct option. So in the previous session we have learned that, and or we can say that we have derived the equation for the magnetic field at a point on the axial line of a current carrying loop, which was equal to B was equal to mu naught n I R square divided by 2 in bracket capital R square plus R square small r square to the power 3 by 2. Now here capital R is the radius of the current carrying loop. R is the distance of a point on the axial line of the current carrying loop from the center of it, and I is the current which is flowing in the loop. So here we have to find the ratio of magnetic field at a very far distance, which is equal to R from the center of the loop on the axial line to that at the center of the loop. So now the magnetic field at the center of the loop, let us say this is, I am denoting here as B center, this is equal to mu naught Ni divided by 2R, where N, capital N, is the number of turns, I is the current which is flowing in the loop, and R is the radius of the loop. Now here, since R, small r, is very large in comparison to the radius of the loop, because here this distance which is equal to R on the axial line of the current carrying loop is located at a very far distance from the center of the loop. Therefore we can say that this R, small r, is very large in comparison to the radius of the current carrying loop. So in this case, this capital R can be omitted from this equation. So we can find the magnetic field at the point which is located at a distance R from the center of the loop and on the axial line. So this will be equal to, say it is equal to B. I'm just denoting here as B axial. So B axial is equal to mu naught Ni R square divided by, since small r is very large in comparison to capital R, so this capital R can be omitted, and finally I will be getting the relation here as R square to the power 3 by 2, which is equal to R cube. So 2R cube. Now we have to find the ratio of the magnetic field at a this distance R from the center of the current carrying loop, and this point is located on the axial line of this current carrying loop to that at the center of the this current carrying loop. So the magnetic field at the center of the current carrying loop is equal to mu naught Ni upon 2R. So B axial divided by B center. Now this B axial is the magnitude of the magnetic field at a distance R from the center of the current carrying loop and lying on the axial line of it, divided by the magnetic field at the center of the current carrying loop. So this is equal to mu naught n I r square divided by 2 r cube divided by this value. So this will be equal to mu naught n I r square divided by 2 r cube divided by mu naught n I upon 2r. So here this value will be equal to mu naught n I r square divided by 2r cube into 2r divided by mu naught n I. From here this mu naught n I will get cancelled out. Here 2 and 2 will also get cancelled out, and finally the ratio is equal to capital R cube divided by small r cube. So here the correct option is A. So thank you very much for joining this session. In the next session I will be coming up with a different type of a question from the same topic. So till then, have a nice day. Bye.